Hello, I'm Destin, and I'm going over my project Linear Oscillating Cylinder and Still Fluid, which was my final project for the Georgia Tech CFD class. To validate the results of my project, I looked at the research paper Simulating Incompressible Flow on Moving Mesh-Free Grids by Dr. Alexeyev, in which a solver was developed and it was used to test the flow around an oscillating cylinder verified with prior experimental and numerical results from other studies. I use the same geometry as this paper, shown in the top right, and in the bottom left, that's the horizontal velocity profile results from the study, which I'll compare with mine. I used a cylinder cross-section surrounded by a square with side length 2D. I used the ALE moving mesh math in COMSOL with the Winslow smoothing method. And the Winslow smoothing method was important given the relatively large deformations to get it to converge. And I also had these 4 diagonal lines to help the mesh quality. I made all the parameters dimensionless and had a no-slip boundary condition on the walls and the cylinder boundary. I used the same Kc number and amplitude to diameter ratio as the prior study to compare. I used d equals 1 and then that 0.2 amplitude for the ratio and a mu of 1, and the prescribed displacement caused a U max of 1, meaning that the Reynolds number is just equal to the fluid density, making it easy to control. I use an unstructured triangular mesh with the Winslow smoother, and I have the parameters on the right of the text there, but when you run the smoother, then it redoes your mesh. And I used 10 periods of oscillation so that the initial values didn't mess with the results. I used quadratic discretization of velocity, and the example convergence and time step plots for Reynolds number of 10 are at the bottom of this page. Looking at the horizontal velocity profile at the vertical center line for Reynolds number of 10, you can see that my results on the left match closely to the published results on the right. Also, all of the period positions correspond correctly to the left and the right plots. That also holds true with the Reynolds number of 100, Reynolds number of 400, and Reynolds number of 1,000. I then looked at the mesh by doing a study of changing the max element size, which is a driving factor in the mesh appearance, with 0.06. That's the one that I used. It had the lowest average difference from the published results to my results. I highlighted outliers. At the top right, you can see with max size of 0.06 versus the finer max size 0.04 and coarser 0.12. I plotted the same data that was in the tables on the last page, and you can see that for 0.06 and 0.12 max element size, it matches very closely, and 0.04, which is the finest one, had inaccuracies, meaning it was probably too fine. And I'm going to play the velocity and mesh animations. So the red means it's moving to the right, and blue means fluid's moving to the left. And this is the mesh skewness. Green means less skewed, and red is worse quality, more skewed. All right, that's all. Thank you.